know that there are two types of physical quantities. One which we call a scalar, where we do not associate any kind of a direction, we just have a magnitude associated with the quantity. And some of the examples are area or length or mass, temperature. So these are quantities that are completely described once the magnitude of the quantity is known to us. So what is the area? You know, it is some square units. So once you know that, you completely have the knowledge about area of a certain space or a certain region. Okay, so that is a scalar quantity. And some quantities have a direction associated with them. Those are called vectors. So usually quantities like uh, velocity. So velocity is analogous to speed, which is also specified by, along with the speed, if you specify direction, you get to know the velocity. So usually like for wind, you would like to know what is the velocity of the wind rather than the speed, because speed is only giving you some information about how fast the wind is moving, but it is not telling you in which direction it is moving. So we can get a complete knowledge if we know the direction as well. Same with the vehicles and all. If you know the velocity, then you would know in which direction your vehicle is moving. So when you have a direction associated with a physical quantity, you call it a vector quantity. So there are these two broad physical quantities. Classification is, one is a scalar quantity, one is a vector quantity. Vector quantity will have a direction along with the magnitude. So not just the magnitude but the direction also. So some more examples are acceleration, force. So force also, you would have noticed that when you are applying force, the direction of force also matters. It is not just the magnitude of the force, but in which direction the force is being applied, that also makes a difference. So this quantity is completely described only when you mention the direction of this particular physical quantity. Okay, and displacement is again telling you how much distance a certain object has moved in a specific direction. So it is not just telling you the distance moved or traveled, it is also telling you the direction in which the distance has been traveled. So we need them. So for example, if you have to measure the distance traveled by a person, but in a I mean, if the shortest distance has to be measured, you just measure the starting point and the end point. But if there are some changes in the direction, then obviously you have to see how you have to calculate the actual distance moved. Okay, so the direction of the distance traveled would also be useful for some cases. So there you need the concept called displacement, where you are also noting the direction of the movement of the object uh, along with the uh, actual distance moved. Okay, so this is broadly the classification of physical quantities into two categories. One category is a scalar and one category is a vector. Okay. Now vectors are represented geometrically by arrows in 2 space or 3 space. Direction of the arrow is going to give you the direction of the vector. Length of the arrow will describe the magnitude. So if we are denoted a vector in the geometrical way, then we can use the arrow to get the direction, which direction it is moving, say north or maybe south or east or west. So what is the direction? Second thing is, what is the length of the arrow? So length of the arrow is describing the magnitude of that physical quantity. Okay. Tail of the arrow is called the initial point and tip of the arrow is called the terminal point of the vector. So these are some terms which we use, and we say two vectors are equal or equivalent also is another term which is used if they have the same length and the same direction. Okay, so in that case we will write vector v is same as vector w. So all these vectors are identical or equal. Okay, because you can see they are moving in the same direction, they are parallel to each other, so they are moving in the same direction, and their length is also the same. Okay, so these are vectors that are equal or equivalent to each other, and you can also say they are translations of one another. So if I just pick up the initial point of the vector from here and translate it here, I'm going to get the other vector, which is a translation. So translation means if I shift the initial point to somewhere else, what is the new vector which I get? So if you see the new vector which you are getting, it is actually equal to the original one, and geometrically you can see visually what this means is that it is going to have the same length and the arrow has to be in the same direction, or you can see that they are placed parallel to each other. Is it clear till this point? What are equal vectors? Yes. Okay. So this part is your initial point. Okay, this is also called the tail or the initial point, and this is the tip of the arrow or the vector. Okay, or the terminal point. So these are initial, this one is initial, and this is the terminal. Okay, because we are not having different vectors. I mean, if we just translate one vector to another place, we get another equal vector to it. So initial point can be moved to any convenient position by making any appropriate translation. So if you want to study a vector somewhere else, just shift the initial point to that particular position and you get a same vector translated there. So the translation is not going to affect the vector, because you are just lifting the initial point to somewhere else and direction remains the same, magnitude remains the same, so you are going to get another vector which is equal to that. Okay, and if the initial point is a and terminal point is b, then we can also write the vector v as ab. Okay, so this is also another notation for a vector where you can use the initial and the terminal points to denote the vector. And if the initial and terminal points coincide, then this vector has a zero length. Okay, and this vector is called zero vector. So you would find either the alphabets or the vectors given in bold, or there is an arrow on top of the vector name. So this is denoting a zero vector, this is denoting vector v. So if you put an arrow on top, so usually when we write like manually, we use a arrow on top of the alphabet to denote that it is a vector, and in books you would find that vectors are denoted by bold alphabets or bold numbers. Okay, so zero vector will be just given by the number 0 in bold. So in books when you're printing, then you can do it, but manually when you're writing you should use an arrow on top so that it distinguishes it from any other physical quantity which is not a vector quantity. Okay, so vector quantity is denoted by the alphabet with v on top, and zero vector, when you have a zero vector, obviously there is no direction associated because it is just a dot, and you can put any convenient direction depending on the problem. You may assign any direction to that particular vector. Okay, so there is no specific direction, or you may say that zero vector has magnitude 0 and arbitrary direction. Okay, so that is another term which you may use. Then there are some operations on vectors. So to start with, how to find sum of two vectors. So I'll just explain geometrically first. If you have a vector v like this and you translate your vector w in such a way that initial point of w coincides with the terminal point of v, then sum of these two, u plus v, is denoted by, geometrically it is denoted by the third side of this triangle whose initial point coincides with the initial point of v, terminal point coincides with the terminal point of w. Okay, so this is how we geometrically denote sum of two vectors. Okay, so you can see that this is also sum also coincides with the diagonal of a parallelogram. So this is another way of giving the sum. If you make a parallelogram whose adjacent sides are given by these two vectors v and w in the same manner, then this third side of or the third side of the triangle is actually the diagonal of the parallelogram, which is determined by these two adjacent sides. Okay. And obviously they uh, should be placed like this. So if you look at this side of the parallelogram, then you can see that the side here is identical to w. So in this placement you can also say that your v and w have same initial points. Okay, that is another possibility. Suppose if your v and w are placed such that they have the same initial point, then you can just complete the parallelogram and take the diagonal that is going to represent the sum of these two sides. Or if your vectors can be placed like this, then you can just see the third side of the triangle, which is formed by these two sides in this manner, and that third side is going to give you sum of these two vectors. So these are two ways of viewing the sum in a geometrical way. And in case you have one of the vectors as 0, so since initial and final will coincide, so actually there will be no w here. You will just have a dot here which is same as the terminal point. So your v vector will be same as v plus 0. Okay, there will be no third side of the triangle because you do not have any magnitude or any length of this particular vector. So it will be just a dot, and so your v plus 0 will be vector v itself, in whichever order you want you may take. So the commutativity rule holds here. V plus w is same as w plus v. So you may add in any order you want to and you would still get the same vector. So you can see that geometrically here also, like if you add w, place w first and then v, the sum is given by this diagonal. And when you place v and then w in this manner, then again the sum is given by this particular diagonal. So in both the cases it is the same diagonal, and therefore v plus w is same as w plus v. So is the concept of sum clear?
Are these vectors equal in length?
No, they may be different in length. That is why the word parallelogram is
representing v plus w.
V plus w is
like a way of representing.
Yes, way of representing the sum. V plus w is this diagonal of this parallelogram, and we are using this to represent the sum of these two vectors geometrically. Okay.
So like if length of v vector is 2 and length of w vector is 3.
Yes.
So it doesn't mean that the third length will be v plus w will be 5. It doesn't mean that, right?
No, you will have to use the the size, I mean the equation or the expression of the vectors to find the actual length. Okay, so suppose let me see if I have some examples. No, so I'll just take up one example here. Suppose if v vector is given by okay, I'll have to still come up, but suppose it has two components. Okay, and say w vector is because I haven't done yet magnitude, let me take, say, okay, what is all those who know how to find the magnitude, what is length of v or magnitude of v? By definition it is 2 square plus 3 square. Okay, and otherwise if you visualize this v, when we draw this geometrically, this is one way of, sorry, so how you can draw is, you can just take the initial point to be at origin and terminal point at 2, 3. So just mark 2 units here and 3 units here, and this is your vector v. Okay, in the same manner you can also mark your vector w 4 comma 7. So that will be the coordinates of the end point, and initial point has coordinates origin. So you can take 4 and 7. This is the terminal point, so just join origin to this point. That is how these two vectors will be represented geometrically. Now if you have to find the length of this vector, how will you find this? This has coordinates 2 comma 3. Initial point has coordinates 0 0. What is the length of this line? Use the distance formula. So root of 2 square plus 3 square, that is going to give you the length of this line. Is that fine till here?
Yes, ma'am.
Yes. Okay, now suppose if we have this vector, now if we translate, the vector w is having the same initial point, but we do not want it to have the same, we want it to form like this. So we will have to shift your so otherwise it is like this, inclination may be slightly different. So if you want to shift this w in this way, so you will have to translate the initial point to this point. Okay, so it may go then I mean when you're shifting it parallelly, so maybe slightly bend, I don't know exactly, so somewhat like this. So this would be a v, this would be a w. Sum of v plus w is given by this third side. Okay, geometrically. And analytically if we want to find, so one is the concept of magnitude. So magnitude of w would be square root of 4 square, which is 16, plus 7 square, 49. This is the magnitude of w. And when you take the sum of v plus w, so algebraically the sum of the first components would come first, 6i plus 10j. This is how you find the sum analytically. And if you want to see the magnitude of this, then you will again use the distance formula, and it will be square root of 6 square plus 10 square. Okay, and here you get root of 65. Okay, so these are the individual lengths, and this is the length of the sum, and you can just compare how the, I mean any such relationship, so that will not hold here as such, because this is the distance. You can see that there is a slight, obviously the slope is different, so these two lines will be slightly, there will be some angle in between, and when you join, so this is your v plus w, so obviously it is not equal to numerical v plus w. Okay, this length will be different from that. Is it clear now?
Yes, ma'am.
What you wanted to ask, so maybe we can take up some more questions later.
W, like the starting point is changed. So like how will it be represented? Like that only v 4i plus 7j.
No, then you will have to represent, I mean it will come out to be this only, the expression for w will be the same, but the arrow will be differently made. Okay,
So like how starting point can we represent that the starting point is not origin?
okay, I'll just wait. See, for a vector w, suppose I'll take the same expression. Four I plus 7j. Okay, now when you are plotting it, in only w when you are plotting, so you may make the graph like this. Starting point at origin and end point at 4,7. So somewhere here, just connect it with the line. This is your vector, okay? Now when you have to show both v and w in the same graph, then v is 2i plus 3j. Okay, so we will have starting point at origin and end point is at 2,3. So somewhere here, let me just take something else. Let me take, let me take 2i plus j, because these two lines are very close. So I take a point here. This is my vector v, okay, and this is my vector w. Now when I have to add them, and if I want to represent them as two sides of a parallelogram, or if I have to translate, okay, how will I translate is, I will lift my w from here, okay, just this vector w I'm going to lift from here parallelly. I'll just shift it parallelly, and so this is the shifting done parallelly. Now I will move its initial point at the terminal point of V. Okay, this is how my W gets shifted. Have you understood how you have translated?
Yes, ma'am.
Yes. So now your W comes here. So we want to shift it in such a way that its initial point coincides with the terminal point of V, or you can do the other process, shift it like this such that both have initial points same. Now if you notice at the W equation, so any vector W here is represented by, so initially when we had drawn it, it was represented by 2 points, or the starting point was origin, end point was say some point A, whose coordinates were 4,7. This is how we represented initially, okay, and we said this is equal to 4i plus 7j. Now second time we are going to represent W as starting point is some, say I call this A1, and say end point I call it A2. Now if I do that translation and I get a new pair of initial and terminal points, then how to get the expression for W? So the expression for W, or these two components, will be obtained by taking anyone knows this? How do we find W from these 2 points?
Will it be A2 minus A1?
A2 minus A1, or you can also say OA2 minus OA1. Okay, this is how you can represent. So if we find, or if we see what is A2 and A1 first, we can see what are the coordinates. A1 has coordinates 2 comma 1, which is the same as terminal coordinate of W, and when I'm shifting it parallelly, what do you think will be the end coordinates of A2? The coordinates of A2 endpoint, what will they that be? So this was my initial positioning. This is the new positioning. If I am lifting my x coordinate, I am increasing it by 2 and my y coordinate increases by 1. How will the coordinates of the terminal point change? Coordinates of terminal point here are 4, 7. Initially I wrote my w like this. Okay, now I'm just translating it here. So what will be the coordinates of the terminal point A2? This was A.
It's 6, comma 8.
6 comma 8. So how did you know that? You have increased your x by 2 units. So horizontally you have moved 2 units. Okay. And vertically you have moved 1 unit. So when you look at coordinates of A2, it is 6 comma 8. Okay, so your A2 is 6 comma 8. Now if I have to give W in terms of A1, A2, what will be the vector equation or what will be the components in this form? So it is, by definition, it will be OA2 minus OA1, or these two vectors we are going to take the difference. So how do we denote the vector OA2? It is given by from origin to A2. So how do you denote it? It is 6i plus 8j. And so we are using the vector notation, ij notation, and OA1, that is given by this vector. It is having the same as V. This is the representation, so that is 2i plus j. Okay, so when you take the difference, what do you get? 4i plus 7j. So it is the same representation, okay, as we had started. Doesn't make any difference how your initial and terminal points are changing. Okay, when you translate a vector to somewhere else, it will have the same components in the horizontal and vertical direction. What will change is initial point and terminal point. That is why we say that these two vectors are identical or equal. Okay, so when you complete this parallelogram, then the diagonal of this parallelogram is going to give you the sum. Okay, so just join this with this. Let me use a straight line. Wait. Okay, this diagonal is going to represent the sum of V plus W. Okay, the diagonal of this parallelogram. And if you see here, the A2 coordinates of A2 will represent the the terminal point of the diagonal. So in terms of vectors, if you find the vector V plus W, it will be represented by the vector OA2. Okay, and the components are 6i plus 8j. So you can see it is nothing but sum of the components of V and W. First component, if you add up, you get 6i. Second component, when you add up, you get 8. So it is nothing but your vector OA1 in the vector form, okay, plus OA, OA. Okay, this was V and this is W. So this is how you find the sum. And if you look at the magnitude, then you can see what is how the magnitude is changing. So magnitude of V, we have already found, it is root of 2 square plus 3 square, that is root 13. Magnitude of W, that is root of, sorry, it is 2 square plus 1 square. I have changed it. So it is root 5. For W, magnitude is 4 square plus 7 square. So that is 16 plus, you have 49, 65. And magnitude of V plus W. So your V plus W is this, magnitude is root of 36 plus 64, so that comes out to be root of 100, which is 10. Okay, so one vector has this length, one vector has this length, and their sum has length 10 units. Okay, so as such we cannot just add the lengths of these two vectors because their sum is given in a different direction. So that is why these two quantities have some direction associated. Okay, so it is not a simple physical quantity which you are adding, it is a vector quantity. So the magnitude is not going to be simply the sum of the magnitudes of these two quantities. Okay, so is all this clear?
Yes, ma'am.
Okay.